Hello, welcome back everyone. This is Dr. Hopkins with your next video. Here we're going to briefly introduce a concept of reactivity around complex formation in Lewis acidity and Lewis bases. So we're going to start with this idea of a different definition of acids and bases. So I think we spent a third of the semester now talking about Bronsted-Lowry acids and bases, those that are proton donors and proton acceptors. Now, there are other definitions. In this case, we're going to talk about the Lewis definition, which is an acid is an electron pair acceptor. So in other words, deficient of electrons and wants to accept a pair of electrons to form a bond. And a base is then the electron pair donor. So anytime you have acid or base, you have a donor and an acceptor. And I'm giving an example. It's probably not the best example, but it does coincide with the Bronsted-Lowry, how they match the acids and bases. So here we have ammonia with our our lone pair electrons. It's a Lewis base. It's also a Bronsted-Lowry base, because remember it was one of our weak bases that we dealt with. So it has those two electrons it could donate. And then a proton is a Lewis acid because it has no electrons and it would accept two electrons to form a bond. So you have the Lewis base and the Lewis acid, which coincide with a Bronsted base and a Bronsted-Lowry base and a Bronsted-Lowry acid. And they form NH4+, which would be your conjugate acid of the base in our previous language. Sometimes Lewis acid, the product of Lewis acids and bases are called adducts. That's not always true, but you'll see it in books. But here's an example of a Lewis acid and Lewis base. Now, why are we learning that? Because we already know what those are in terms of Bronsted-Lowry. And it turns out that, we didn't do any transition metals because it's very hard to pigeonhole a transition metal in as a Bronsted-Lowry acid. Think about it as a proton donor. It just doesn't make any sense. So many of these transition metals actually act as Lewis acids, and they're going to react with Lewis bases. So it gives us a different type of reactivity called complex formation. So the product of the acid and base, in this case, is a complex. And here we have an example. This should be familiar from one of the first videos of the semester, where we have silver plus is our Lewis acid, and NH3, or ammonia, is our Lewis base. It combines with two of those to form the complex the silver ammonia complex. That should actually be aqueous in that case. And the equilibrium constant for that is called a formation constant, Kf. And I looked it up in our book, and it's 1.7 times 10 to the 7th. I've actually looked it up online in other places. It was 1.1 times 10 to the 7th, what I used earlier in the semester. I also saw 1.6 times 10 to the 7th. I don't know what the exact correct number is if you measure it, but either way, it's actually a very large K. Okay, so it favors products. So this formation is favored, thermodynamically favored. So if we were to want to know how much complex we formed, we'd basically treat this like stoichiometry. We would say it's 100% completion, which one's my limiting reactant, and then how much silver ammonia would I get. If we wanted to know how much silver is left over or how much ammonia is left over after the reaction, we'd have to go back through and do an ice table. And there are examples in your book. I'm not going to do one here. We've done plenty of ice tables. We do plenty of them in class. But that's how you would go about doing that. So why do we learn that? Well, other than that it's a different kind of reactivity, so it's a new kind of reactivity. There's lots of chemistry going on. We just talked about solubility. So let's think about how this would impact solubility. So aluminum hydroxide is an insoluble salt. And we know that because we could look at our solubility guidelines and see that hydroxides are insoluble. Or we could look up the reaction and see that it has a KSP of 2 times 10 to the minus 32. Okay, so this is the neutral aluminum hydroxide is a solid, and it doesn't dissolve very well. It's 2 times 10 to the minus 32 is pretty much all reactants. So if we were to write this the other way around and say, well, let's do a precipitation. If we want to get rid of aluminum from our solution, for example, if we mixed aluminum and hydroxide at a 1:3 ratio, we'd get a precipitant. The aluminum hydroxide would fall out, we'd get all of it, and we would get our aluminum hydroxide solid out. But turns out, if you mix aluminum with 4, so in a 1:4 ratio, you get a complex formation. This aluminum hydroxo complex, which is a negative ion, and it has a formation constant of 1.1 times 10 to the 33. So you very much get a soluble complex, not an insoluble salt. And so if you were to accidentally overshoot that ratio, so if you're trying to you're trying to precipitate out all the aluminum, and you overshoot with your hydroxide, you'll end up with a soluble complex, not an insoluble salt. Okay, but they're different kinds of chemistry, but both of them have an equilibrium or thermodynamic aspect. So in this video, we basically learned a new definition of acidity and basicity. It's Lewis, so it's electron pair donors and electron pair acceptors. We know that transition metals often act, or we can treat reactivity of transition metals as Lewis acids, Lewis bases, and form complexes in solution. And what we didn't talk about, but what you're going to find out if you take more chemistry down the road, is that Lewis acidity and basicity is actually pretty important for describing reactivity in your other chemistry courses, such as inorganic chemistry. So until next time.